In this video, I'll show you how to solve the ALEKS problem called Finding Atomic Mass from Isotope Mass and Natural Abundance. So this problem's got a story which you can completely ignore, focus straight on the data. It's telling you that there are two isotopes of the element Sn, which is tin. One of them has a mass number of 120, one of them has a mass number of 118, and it's giving you the exact masses of these isotopes in AMU. It's also giving you the relative abundance of these isotopes. So this is telling us that of all of the tin, 41% of it is this particular isotope, and 59% is this isotope. It wants us to use this information to complete a periodic table box for tin. So it wants us to make something that resembles the box on a periodic table. Now, on a periodic table, in the top portion of the box, sometimes it's in the top corner, sometimes it's straight up in the top. This is where we write the atomic number for the element, which is going to be the number of protons. And then in the bottom portion of the box, whether it's directly underneath or sometimes it's off to the side, this number right here, this is the average mass of that particular element. The average mass is based on this data that's given to us in the data table in the problem. The first thing that we want to fill in is the number of protons, because that is the same for all elements regardless, so all of the elements of tin. So what we want to do is use a regular periodic table, and we want to look for tin, that is Sn, on the periodic table, and we're going to use that to figure out the number of protons. So we can see that the number of protons for tin is 50, and that's going to go into that box. Now you might be thinking, oh, like, is it really this easy? Like, we're just going to copy all of the information. So we're going to take this number and put it down here. Of course not. It's not that easy. This data up here is not real. If you actually read the story, it's talking about this is coming from some planet other than Earth. So these relative abundance values are not the same as what is being used to calculate the 118.711, so that you can't put that number in the box. You've got to do some calculations. The average mass is by taking, the average of all of these masses. The easiest way for you to do this is to just simply multiply the relative abundance. So that's going to be 41%, which is the same thing as 0.41 if we do it in decimal form. 0.41 times that particular mass of that isotope, 119.90. And we're going to do the same thing for the other one, 59%, if we do it in decimal form, that's 0.59 times the mass of that isotope, 117.90. And we want to add these, we're going to add these two together. So I'm going to pull my calculator up here, and I'm going to do each of these individually, do the math individually. 0.41 times 119.9, that is 49.159, and 0.59 times 117.9, that is 69.561. And then I'm going to add those two numbers together. 118.72. When you get this number, it should be pretty similar to the number that's on the periodic table. It should not be identical, but it should be pretty similar, and it should also be pretty similar to these mass numbers that we have for these elements. Now, last thing we want to do before we put this into ALEKS is just make sure that we're using the correct number of significant figures. Here it tells us to round our entry to 3 significant digits, which just means that I'm going to just chop off all of these decimal points over here. The first 3 numbers, paying attention to the 7, which means I'm going to round the 8 up to a 9. So this is going to be 119, and ALEKS always wants us to put a decimal point at the end, even though that looks super awkward. That's the format that it wants, so that's how you'll solve this problem.